Okay, so what we have seen already is we introduced the rules that you see here in front of you for the derivatives for bases other than e. And what we want to do in this lesson is practice a little bit using these and applying them in a variety of situations, and then also introduce integrals. Okay? Before we get to that, though, let's talk about this example here, just as kind of a warm-up. One of the biggest mistakes students would make when doing this type of a derivative is trying to use the power rule, okay? But we can't use the power rule in this case because our exponent is not numerical, okay? So we have to do something else, all right? So they give us a little bit of a hint here. Use logarithmic differentiation to find dy dx, okay? So what do they mean when they say use logarithmic differentiation?
Log of both sides.
Yeah, take the log of both sides first, and then that'll help us a little bit, okay? So I'm gonna do ln of y equals ln of a 1 plus x to the 1 over x power. And remember, this is helpful because now that I have ln of that 1 plus x to the 1 over x, I can pull the exponent outside. Okay? So I have 1 over x times ln of 1 plus x. And then that equals ln of y. And it's at this point that I would go ahead and find, or actually take, the derivative. Okay, so now I'm going to take the derivative. And the derivative of ln of y is going to be the dy dx, or y prime over y. And then on the right-hand side, I'm going to need to do my product rule. Okay, so the derivative of the first is a negative 1 over x squared times ln of 1 plus x plus the first, 1 over x, times the derivative of the second. So the derivative of the second is 1 over 1 plus x. Okay, so there's my product rule. And not a ton we can simplify at this moment, but we do need to finish solving for y prime. So we need to multiply both sides by y, and we get that y prime equal to ln of 1 plus x, we'll put that over negative x squared, plus 1 over x times 1 plus x. And that whole thing will then be times the y. Well, the y was a 1 plus x to the 1 over x power. And there's our derivative. Depending on what we want to do with it, we may simplify in other ways or whatever, but there we go. Okay? It's a little bit of warm-up, getting our minds going with that. Okay? So, let's now look at applying these rules. Just a reminder, remember that instead of e to the x, we have a to the x, but the rule is very, very similar. The derivative of a to the x is a to the x times ln of a. The derivative of a to the u is a to the u du dx times ln of a. Okay, so it's the same rules as e to the x, but you're multiplying both of them by the ln of a. Okay, and then with the log, a log with a base other than e, it's going to be 1 over x times ln of a. Notice it's in the denominator. And with a log base a of u, it's 1 over u ln of a times du dx. So again, we have the chain rule there. And by the way, I can't remember if I pointed this out to you guys specifically, but these rules actually do still apply even when the base is e. If you think about it, if I have the derivative of e to the u, it's e to the u du dx, right? Times ln of e. What's ln of e equal?
1.
1. Okay? So it works even if you have an e, it's just unnecessary when you have the e because it works, comes out to 1 there. Okay? And same thing with the log rule. Okay? So just a little connection there. So let's actually practice using this a little bit. Okay? What's the derivative of e to the e?
It's just derivative of 1.
What is it?
Wait, no, it's not 0.
It's 0. What's e to the e? It's a constant, right?
Yeah.
Start you off with a trick question. Not really a trick question, but be careful. So then the derivative of e to the x is e to the x. Okay? How about x to the e? Yeah, e is a constant, right?
Yep.
We can use the power rule. E x to the e minus 1. That's our power rule. If it's x raised to a power that's numerical, then you can use the power rule. So then here we have y equals x to the x. And this one we've got to use that logarithmic differentiation. Okay? So we have ln y equals ln of x to the x. Ln of y then equals x times ln of x. And now we can take the derivative. Okay? Y prime over y is 1 times ln of x plus x times the derivative of ln of x. So we have ln of x plus 1. And I got to multiply both sides by the y. Okay, so if I'm multiplying by y here, I'm going to multiply by x to the x over here, because they're the same thing. So I then have this times x to the x. And again, how you choose to simplify that is kind of up to you. If you wanted to get really fun, if you distribute this x to the x times ln of x, think about your rules with the logs. You could pull the coefficient inside the ln, right? And that'd be ln of x to the x to the x.
Oh, yeah.
That looks fun, doesn't it? But I wouldn't do that. Just because you can doesn't mean you should. Alright, so, anyways, you could go ahead and do that though. Alright, so a little bit of practice with, I don't want you to forget rules that we've learned in the past, and don't just assume every time you see an E it's going to be, you know, the same rule. Be careful of, hey, what's my base, what's the exponent? And every one of these required a little bit different of a strategy. Okay? So, that kind of brings us here to our integrals. Our integrals for bases other than e. Okay? Now, if we're doing the integral of a to the x, that's going to be 1 over ln of a times a to the x. If you think about what we had before, it was the integral of e to the x was e to the x. Okay? We also had the derivative of a to the x was a to the x times ln of a. So if we're going in the reverse, okay, if we're going in reverse here, it makes sense that we have to have a 1 over ln of a, because then when we multiply by that ln of a, it's going to cancel out. Okay? It's kind of like when we were doing the reverse of the power rule. You add 1 and then divide to the exponent and divide by the new exponent. So it's kind of a similar concept here. But this is our rule for the integral of a to the x. It's 1 over ln of a times a to the x plus c. Okay? Now we can derive this if you look at the this little tip here that they give us. Okay, let's actually do the derivation of this. We have the integral of a to the x dx, and that's equal to e to the ln of a. We saw that when we derived our derivative rule. Okay, we have that to the x power. Well, I could rewrite this as e to the x ln of a dx, and now I'm doing the integral of e to the u. Okay, so how do I do that? I have to do u substitution. U would be the x times ln of a. What's du? Not product, because ln of a is a constant, right? So it's just ln of a dx. Okay? So, notice what I need. I need an ln of a inside, so I need a 1 over ln of a on the outside. Okay? Now I have 1 over ln of a, and the integral of e to the u is e to the u. Okay? Remember that this is our du. So the integral of e to the u du is e to the u. So it's e to the x ln of a. Okay? We can kind of rewrite this again. 1 over ln of a times e to the ln of a to the x power, and e to the ln of a equals a. Alright, so it's 1 over ln of a times a to the x, and now we'll throw in the plus c. Okay, so this is where this rule comes from. So let's use this a little bit, okay? So if I want the integral of 2 to the x, the integral of 2 to the x is going to be 2 to the x over the ln of 2, yeah, plus c. Okay? If I have 5 to the negative x, let's think about this. We're saying, this is what Adam said, 5 to the negative x over ln of 5. What do you think? Yeah. Okay. We should have a negative, and this is why. The u, this is 5 to the u, right? So the du would be a negative dx. So I do need to incorporate the negative here, which means I need a negative on the outside. So that means our answer will be negative 5 to the negative x. Okay? And how about this one? The integral of 3 minus x times 7 to the 3 minus x squared dx. Okay, let's make our u the 3 minus x. So du is -1.
Yeah.
Now, how do you think that's going to work here?
You have to add a negative.
Can you do two U's or not?
Hmm?
Can you do two different U's? Like two, the same one, but like two U's.
Well, you just need a -1.
Potentially.
Yeah, but I get what you're saying. Like there's two.
Let's look at what happens here, okay? Let's look at what happens here. If I incorporate a negative on the in and the out, I have negative integral of u times 7 to the u squared du. So did that help us?
Yeah.
Just make v minus x squared.
Aha. Okay, say that again, Nate.
Just the whole exponent make the u, give it a squared in it.
Okay, yeah, let's go ahead and incorporate the square into our u. Okay? Make that whole thing 2 times 3 minus x to the first times a -1 would then be our du. Okay? So we're going to use the chain rule here. So we have 2 times 3 minus x to the first power times a -1, chain rule. And now what that means is I don't just need a negative, I actually need a -2 here and a -1/2 on the outside. Okay? Because this and this all combined are the du. Okay? So again, you gotta be careful with this. So now notice what we have. We have a -1/2 7 to the u du. Okay? That's a lot more easy to handle. Okay? So what's the integral of 7 to the u du?
7 to the U, 7.
Yeah, 7 to the u over ln of 7. Okay? How we choose to simplify at this point is kind of up to you. So we have a -7 to the u over 2 ln 7. And I could go ahead and, I need to substitute back in the 3 minus x squared. And I could, if I wanted, make the bottom an ln of 49. Pull the 2 in as a square. Okay? Again, how you choose to simplify, that's kind of up to you, but
Would you need to find a number? It wouldn't really matter.
like as a decimal?
Yeah.
No. No. Really, unless you're specifically told to find something to so many decimals or whatever, you can always leave your answer in terms of ln's or pi's or whatever. Radicals. Okay? Alright. So that's it for that. It's just a little bit of practice using this form. Don't forget the u substitution, just like what we've done in the past. If it's not something to the x, then you're going to have to use u substitution somehow when you're doing these integrals. Okay, so we're looking at the integral of 7 to the 3x.
Yeah.
Okay, well in this case the u would be 3x, right?
So you just find U.
So the du would be 3dx, and you'd need a 1/3. Okay? So yes, you got most of it there. It would be 7 to the 3x over ln of 7, but you'd also need the times 1/3. okay?
So this doesn't, the integral,
Oh,
like, rule.
I
doesn't
forgot
work
the plus
for-
C back here too.
The
Oh.
integral rule doesn't work for, like it, for E, it needs a specific X, like only X.
Well, I mean, to use it directly, but it's like all of our other rules. I mean, we recognize that when we see the rule with just an X in there, if we're doing a derivative and there happens to be a U in there, we're gonna have to use chain rule. If there happens to be, if we happen to be doing the integral and there's a U in there somewhere, then we're gonna have to do U substitution of some sort. Okay, just like we did on B and C and then down here. Okay, that's a good question though.